So if you actually go into the open literature, there are lots of different types of fuel cells, lots of different electrolytes used. The original fuel cells were all based on liquid electrolytes. And some of the ones that are quite famous, like alkaline fuel cells used by the NASA missions, for example, they're all during the 1960s. Those are all, available. You can buy one if you want to. However, they haven't really reached a high level of technological success or commercial success is what I really mean. So what I've decided to do is focus the course mostly on the fuel cells that are in active development for commercial applications today. And all of them are solid state. And in particular, there are two types that most people are usually talking about when they're talking about fuel cells. So one is the polymer electrolyte fuel cell, which is based on a Nafion or Nafion-like polymer membrane, which operates less than 100 degrees C or thereabouts. And it's also often called a PEM, which stands for proton exchange membrane fuel cell, or PEM. So you'll see it as PEM fuel cell or PEFC or PEMFC. Those are all referring to the same thing. And the way those work is basically you have a solid proton conductor. That's what the polymer does, is it serves as a solid proton conductor. So on one side, oxygen becomes reduced by incorporation of protons. And that's what you see on the left. So protons are coming from the anode to the cathode. The protons interact with oxygen, forming water, and that consumes 2 electrons. And then at the other side, we're oxidizing H2 to H+. So the fuel sort of disappears. If we're using hydrogen as a fuel, which is the case, and I'll come back to that in a second, H2 is oxidized, forming 2H+, and then that's what goes across the membrane. The other type of solid state fuel cell that's in common development today is the solid oxide fuel cell. This operates at much higher temperatures, upwards of 850 or 900 degrees C in some cases, as low as maybe 450 degrees C, so very hot temperatures. And it's based on a ceramic membrane. So it's a membrane which is a oxide material, and you have a mobile O2- ion inside this crystalline material, which serves as the electrolyte. So in this case, oxygen is reduced on the cathode side, producing O2- as an ion, which then goes through the electrolyte, and then the O2- oxidizes the fuel. So one big difference, and we'll talk about this a little bit, the exhaust for the reaction, in this case H2O, is produced on the fuel side, not on the air side, as it is in a polymer fuel cell. So basically, these are the two basic types of fuel cells that people are trying to develop today. Just to give you sort of a status, where have these things shown up historically? And I'm talking about like looking over the last 15 years or so. Polymer electrolyte fuel cells, some of their features, they are operating at very low temperature compared to a solid oxide fuel cell, less than 100 degrees C, up to, well, I guess up to 120 degrees C in some cases. The materials of construction tend to be less expensive because you're talking about ordinary temperatures. And so you can make things out of metal or things that you would normally make automotive components out of. It's pretty straightforward. The size and weight of these fuel cells is very favorable. They're lightweight. They're relatively small for the power density that they can produce. And so not surprisingly, that has been a major focus for automotive transportation. And that's what you see on the left is a picture of a Honda fuel cell based car that you fill with hydrogen and then it runs on hydrogen gas. Some of the challenges with polymer fuel cells, they require pure hydrogen. So the catalyst materials in these systems are very intolerant to carbon containing reducing gases. Carbon monoxide usually is the culprit. And so any other carbon containing materials that are going to form carbon monoxide in the system, those will poison the catalysts that are typically used in a polymer electrolyte fuel cell. Another issue is because of the temperature of operation being around the boiling point of water, you're dealing with H2O in both the liquid and the solids phase, and it can lead to some pretty complex water management issues in terms of the rest of the operation of the cell. We're trying to get gases to the electrodes, and yet we're producing a lot of water. And so how we deal with all that is actually a major engineering challenge. And one of the things we'll talk about when we get to the stack design segment of the course is like, how do we deal with all the water management in a PEM? Other issues include the degradation of the membrane and the catalysts over time. And then finally, another one, sort of a subtle issue, but it's still a major issue nonetheless, is the difficulty or impossibility of recovering heat. So as I mentioned on Monday, one way to think about a fuel cell is it's combustion process that produces electrical work in lieu of heat. So you're still producing heat, you're just not producing as much. Now you're producing electricity in addition to heat. And if you are running a normal combustion process, you typically try to combust at very high temperatures so that the heat that you generate has high quality and is easy to recover and convert into work. That's not really an option when you're generating the heat at low temperature, like 100 degrees. And so it's difficult or impossible to recover the heat. And in fact, it can become a liability. And just to illustrate that point, this car, if you look at it just in this photograph, you might notice it's kind of weirdly shaped. I don't know, does anyone notice that? What's unusual about the shape of this car? It's not just an optical illusion from the camera angle. The front of the car really is massively big. And there turns out to be a reason for this, because the fuel cell is operating at lower temperatures than a typical engine block operates. The coolant is also relatively cooler than the typical coolant temperatures in an engine block. And so the radiator has to be bigger to be able to handle that and be able to get rid of all the waste heat. And it's kind of, not only can you not use the waste heat in an automotive application, but it's actually difficult. Yet it's more expensive to get rid of the heat because of this lower temperature of operation. And so to really make it work, the polymer electrolyte fuel cell has to be very, very efficient. We need to recover as much as of electrical power as possible in a polymer electrolyte fuel cell, because whatever heat we make, we can't use it. It's only the electricity basically that we can get out of it. Sort of the status today, most developers, have focused mostly on automotive applications. So several of the world's largest automakers have produced at least demonstration units. Ballard Power in Vancouver, Canada, has been here around for a while, producing fleet vehicles and things like that use polymer electrolyte fuel cells. They're probably at this point one of the leaders still in this area. However, one of the things that remains true is this cost. Performance and cost remain sort of not competitive at this stage with other ways of load leveling renewable power, and in particular, electric vehicle hybrids have taken a sort of part way in terms of efficiency. So if you're from the efficiency angle, hybrids actually do a very good job of recovering a lot of the lost work. And so fuel cells are not as desirable in the world in which we have efficient hybrids. And as cars become electrified, as we start to use electric cars and improve the range of electric cars and the availability of electric recharging stations, it may be that transportation applications, which is a relatively smaller scale than stationary power, it may actually be better to treat it as a mobile application that is powered by batteries. So I think the jury is still kind of out about that, but it is a complication to have to handle fuel of, hydrogen fuel as a transportation fuel. It's one of the most difficult applications for the fuel cell. I've always found that kind of ironic that, if you want to pick a really bad and difficult problem to try to solve with a polymer electrolyte fuel cells, it would be cars. It's just really hard. And yet that's been the main effort because of the importance of the transportation sector. So where that's going in the future, I'm not sure. But I will say that the cost requirements for stationary power is much less stringent. I mean, cars are very cheap devices. It's one of the most economically difficult things to make a case for fuel cells. A lot of other applications, you can afford more if you're getting high efficiency and other benefits. Okay, so that brings us to solid oxide fuel cells. The main difference here is they run at high temperature. What that means is they're producing both heat and electricity. And so in particular, in any application where you need both heat and electricity, then you can have very high efficiency. And so it's not surprising. A lot of companies now, like like Solid Power, they produce the BlueGen system. There are other, Kyocera, major Osaka Gas in Japan is making probably the largest number of solid oxide fuel cells at this point, which are going into homes or small apartment blocks. And their basic function is to provide electricity and simultaneously heat hot water or provide heating, at least in the winter. And so you get a lot of sort of these secondary benefits from using the fuel cell and using both the electricity and the heat. Another advantage of a solid oxide fuel cell is that it can run on hydrocarbon-based fuels. Not that we want to do that forever, but certainly as a stopgap measure while we're trying to figure out how to make fuel cells and advance the technology and the supply chain for the technology, there's a lot of arguments to be made that being able to have fuel cells run on natural gas today, hydrogen in the future, is a good strategy. And so SOFCs, they can run on reformed natural gas or other hydrocarbons. And it's all solid state. Some of the challenges: materials stability and compatibility of these ceramic materials. You have thermomechanical stress because of the high temperature and the heating and the cooling. So things where you have dynamic load variation or applications where things have to turn on and turn off, that can be somewhat challenging. Like in a PEMFC, there tends to be electrode and interface degradation over time, which people are still trying to work out. Some of the catalysts are susceptible to certain types of air contaminants, which act as poisons, and it's historically high cost. At this point, if you look back at the last 35 or 40 years of research in solid oxide fuel cells, a lot of it was sponsored by the Department of Energy and has been focused on large-scale power generation. And for years, that was the main focus. So it was all about efficiency and trying to bring the cost down into the range where it could be competitive with advanced turbine cycles and things like that, which are also large scale. And so it's been tested up to like 250 kilowatts. These are fairly large stationary power systems based on traditional SOFC materials that were developed back in the 70s. But it's just incredibly expensive. So we're talking about $2,000 or more per kilowatt of electrical capacity, which is not really cost competitive based on traditional fuels. So and that was the focus for years. I would say though, in the last 10 to 15 years, maybe, kind of in the wake of the polymer electrolyte fuel cell world, SOFCs have started being refocused on smaller applications. So sort of advances in materials and manufacturing that has really brought the cost down, and they've started to make inroads in applications like cogeneration of electricity and heat, like I was describing earlier. So the Blue Gen unit is a relatively cheap home appliance. You can buy it, goes into your house, produces heat and hot water, and it produces electricity and lowers your electricity bill. So for small scale distributed power, it can provide this very high efficiency at small scale that people are looking for. And if we go to a hydrogen network, then it can become 100% renewable power.